Okay. So, all right. So, if you watched, I don't know if you watched the pre-recorded videos, but I have dug a lot deeper into hypothesis testing since I made those. So I'm hoping that this is even better than the recorded videos. Who knows though? So you just never know what I'm going to actually say. I never know what I'm actually going to say until it comes out. So section 10.2, we're going to finish that up. We started it and we talked about the critical value and the test statistic. We talked about p-values a little bit. We're going to dig a little bit deeper. So 10.2, we're going to talk about testing hypotheses with population proportions. This ties in with 9.1 and 8.2 really well to just kind of flow with it. It's using some of the same information, some of the same calculations. And 10.3, so I know you probably all saw the words binomial probability distribution, and you probably all just wanted to log off and go and curl in the corner and cry. You do not have to use binomial probability distributions at all if you don't want to. In fact, usually I just skip over that, and I'm happy to do that again if you'd like, because you don't actually need it. So it's just another way. It's a faster way, but you don't actually need it. So we can just skip that. 10.3, this is testing our hypothesis about a mean. And we're going to talk about, and I'm not even going to talk about statistical significance and practical significance, because those are not really even important. So, yeah, so this is going to be the last of our new material. And Tuesday, we will be able to get together. I will be available from 5:30 to 6:30 as usual for drop-in office hours before the test. And I believe Caleb posted in the discussions about Sunday night, that 5:30, I think he said, there's going to be another Zoom meeting for anybody that wanted to get involved in that for a study group that doesn't involve me. I'm just letting you know what was in the discussions. So if y'all wanted to get together and talk about test stuff. So I love that you guys are doing that. I love that that's happening in this class. There's only been one other class that's happened in, and it just makes me happy. So anyway, that's where we are. Let's move on. Okay, we are in 10.2. So we kind of talked about this already. So a researcher obtained a random sample. They found that 534 were in favor of banning cell phone use. We're trying to determine, does this suggest that more than 50% favor the policy? So I believe like the first 3 slides I have are the same as Tuesday. So statistically significant just means that it is enough, far enough away from the null hypothesis to make it statistically improbable. So we'd end up with a probability that is too small for it to be a happy accident. So that's why we say something is statistically significant. So if there's a less than 5% chance, or whatever our alpha is, of something happening, it's statistically significant, and it tells us that our null hypothesis probably isn't true. And that's kind of where we're going with this. So we are kind of building a confidence interval, and then we're going to be testing whether or not our sample falls inside that confidence interval or outside the confidence interval. That's basically where we're going today. Okay. I already did this whole one on Tuesday, but here I had standard deviation. I calculated 2 standard deviations above and below the mean. And then I'm going to look here at the z-score. My z-score is more than 2 standard deviations away from the mean, yet my confidence interval is just that 2 standard deviations. Since this is outside of that 2 standard deviations, it is statistically significant, and we say the null hypothesis is not true. So I already kind of went over this Tuesday, but it makes sense to do it again. So because this is too many standard deviations away, then we reject our null hypothesis. It's not likely to happen, like by accident or whatever. So we probably don't have a mean of 0.5 or a proportion, a population proportion of 0.5. All right. So it's the same thing, the same type of thing with probabilities. So we're saying if I have a mean of this, if I had a mean of, I think the mean was 0.5, but if I have that mean, so 0.5, what is the probability of getting my sample that I have? And if that probability of getting that sample that I have is smaller than my alpha, which I think is right here. So this sample, this probability is smaller than my alpha. Therefore, it is not likely that this is our mean. It's likely that that value is higher. So that is where we're going today. And I'm going to give you a calculator function also that's going to do this work for you. And it's going to be fantastic. All right. I'm in a good mood today. It's been a good day. Graduation was last night. It was amazing. It was awesome. And, you know, all those kids are off. I didn't cry, but I almost cried. It was really lovely. All right. So this was the p-value one. We're going to just move on. Let's go. Okay. So remember, our p hat is the number of successes divided by our sample size. This is just our reminder. This is called a point estimate, or we just call it p hat. I think, doesn't my open math occasionally call it p star? I think they do. So I'm going to put that here also, because my open math has to be funky and do weird things like that. The curriculum I use at the high school also uses p hat. I had never seen p star before, before my open math did it. But I'm like, okay, you guys, you're a free program. We're going to accept p star and just go with it. Right. So once again, also a reminder that our, when we are dealing with proportion, our mean equals our mean sub p hat equals the p. And this is how we would calculate our standard deviation. This is just a reminder. And all of these things haven't gone away. We still like all this stuff. This is just bringing back all of the previous stuff. I'm hoping you all are getting to almost where, maybe you'll have to refresh your memory a little bit, but this is familiar. This standard deviation, hopefully it's becoming familiar, at least. So you don't look at that and say, what the heck is that? That it's actually somewhat familiar. I'm hoping we're getting there. And this P is the same as this P. So this is the population proportion that they are giving us. It is the same one, or the previous study, or whatever's in our null hypothesis. That's that P. So this P, I'm going to put it over here. P from our H naught, our null hypothesis. That's what that P is. Because that P is going to help give us the values on either end of our confidence interval. So there we go. All right, moving on up. So when we are dealing with population proportion, this is what your hypotheses will look like, our null and our alternative hypothesis. This value, this P naught right here. So whenever you have something sub-zero, it's just called naught. So P naught, that's what that is. I'm gonna write that down. This is called P naught. So when I keep saying it, you'll understand what that means. That right there is whatever value is given to you in your problem. So if it says that the proportion of people who have more than 3 cats in their household, this would be that proportion. So whatever proportion they give you, that's what that would be there. Okay. All righty then, moving on. So The first thing we do is we're determining if we have a 1 or a 2-tailed test, and then we write our null and alternative hypothesis. This is how we start this process. On your test, you are going to be required, I'm telling you ahead of time because I want it to be in your brain, you are going to be required to complete a hypothesis test step by step. I'm going to want you to do every piece of it. So the first thing you are going to do is you're going to write your null and your alternative hypothesis. So in your,
Sorry, can you repeat that?
I'm going to try to mute.
Thank you.
Yeah, okay. So so on the test, you're going to be required to do a hypothesis test and do every single step. So your first step is to write your hypothesis. And it's this one or whichever one, depending on what kind of a test you have, you write your null and your alternative hypothesis. That's your first step, always. So next one, they will give you your, they'll give you your level of significance. They're not going to say the type 1 error, yada, 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 but your level of significance is your alpha. And you'll be given that. You will always be given what your alpha is. It'll say at an alpha equals, whoops, it could say alpha equals 0.05 is your level of significance. It'll tell you what that is. So you're never going to have to choose your own level of significance unless you do a hypothesis test in your final project. Then you'll choose your own. 0.05 is pretty common, and that's probably where I would go if I was choosing one, because it's probably the most common one. So second level of significance is the second piece. Whoops. So as I showed you before, we have 2 different ways to do a hypothesis test. My Open Math will tell you which way it wants you to do it. When you're doing your own, you can choose which way you'd like to do it, letting you know. You choose which one you like best. So the first one I'm going to show you is computing your test statistic. All this is your Z-score.
Please mute your mic.
Yeah, I'm going to try to get it. There we go. This one, all this is a Z-score. This is the Z-score based on your p-hat and your initial value. So that's all it is. It's just a Z-score. The Z-score of your sample.
Ashley, you're not muted.
Oh, the step back this one. Why are they so long?
Try to get, I tried to do it before, but I was not able to get it done. So I can't see everybody. There we go. Will it let me? There we go. All right. Got it. Okay. Once again, the test statistic is just a Z-score of your sample. This right here is your p-hat. This is your point estimate. This right here is the initial value, or the, I guess we can call that initial value given in the problem. And this right here is just the standard deviation. It is sigma sub p-hat. So all you're doing is finding the Z-score. Okay. I'll give you a second to write notes on that. All right, moving on. So this is important, is to determine what kind of tailed tests you have and where your critical region is. Drawing a picture is frequently helpful. So your critical region, if you have a 2-tailed test, you have 2 critical regions. You have one above and one below. Because if your test statistic lands in either one of those, then you have to reject your null hypothesis. So if my test statistic lands in here, then I fail to reject the null. But if it lands in the critical regions, which are right here and right here, then I reject. So inside that confidence interval, you fail to reject. Outside of it, you reject. But on a one-tailed test, you only have one critical region. So on a left-tailed test, you have one below. On a right-tailed test, you have one above. Because anything above your critical region is statistically significant, is too far away from your mean. So on the two-tailed test, just letting you know, you cut your alpha in half. On the one-tailed test, you do not. And I'm just like drawing all over this. Two-tailed tests, we cut our alpha in half. One-tailed tests, you do not. Okay, I'm going to show you the Z table because it's cool and it has stuff for you. Go over to there if I can get there. Okay, let's go the other way. Okay, once again. So once again, at the bottom of my Z table, maybe if I can get there, come on. Okay, went too far. My computer is moving really slow. Thought the batteries were almost dead, but they look good. Okay, it's thinking about it. Come on. Okay. Right to the right of where we found our critical values before, take a look at the hypothesis testing critical values. So it gives you your level of significance right here. So if it's 0.10, 0.05, or 0.01. So on my left and right-tailed tests, they're the same values. They're just positive and negative. Depending on, because if left-tailed tests, remember you're looking for values in the lower end. Right-tailed tests, we're looking for values in the upper end. Two-tailed tests, we have to cut our alpha in half because half is above and half is below. Just like we were doing with our confidence intervals, because we're looking at the middle 95% or the middle 80%. We had to cut that alpha in half. So that's why the two-tailed tests are different. And we need both the positive and the negative z-scores. So this helps for the most common ones, but as before, you can use inverse norm to get those values. You just have to be really careful to determine if you're doing a left-tailed, right-tailed, or two-tailed. Left-tailed will always be a negative z-score. I'm going to write these down. I'm going to go back to my other screen. Okay. I'm going to write this down always negative z-score. Here will always be a positive z-score. And then here you want both positive and negative. So hopefully that'll help you. We doing okay so far?
So I've been using test, one prop Z, and then another one. Do those work, or do you want us to do these?
I don't know what you for chapter 10.
Yeah,
So chapter 10, you're going to use prop Z test.
yeah.
Yeah,
And
you will.
and-
I'm just not there yet. I just haven't got there
Oh.
yet.
okay, thank you.
Just haven't gotten there yet. But you still have to find your critical values. Because if you don't find your critical values, you have nothing to compare your t-value or your test statistic to. So you have to find your critical values on your own. Because the one prop Z test won't give you your critical values. It only gives you the test statistic. So using inverse norm can give you that critical value.
So when using inverse norm, your area, like most questions you'll be given that whatever your area.
Yeah, you're given the alpha, yes.
Yeah, okay.
Yes. So like, for example, I might be given an alpha of 0.05. If I have an alpha equals 0.05. And so if I have so I'm just going to use my inverse norm right now to find out what that would be. And I know it, but I just, for some reason, I just don't trust myself because I could be wrong anyway. So it's 1.645. I have that even memorized. So here, this would be positive. My Z would be 1.645 for my critical value. That's this spot right here. Here, it would be negative 1.645 right there. But on this one, I would have to cut it in half because it is a two-tailed test. So I would have to use inverse norm with 0.025, just like we were doing when we're doing centers. And then this would be negative 1.96 and positive 1.96. We'd need both of those values because this is a two-tailed. You have to cut your alpha in half.
So when you cut it in half, it increases or decreases the value of the Z-score?
The Z-score is going to be larger because like if this right here is 0.05 and this right here is 5, like both of these are 5%, then these are that cut in half. So these are both 2.5%, right? Because I had to cut it in half because it's a center.
My mind just thinks that the Z-score should literally be like cut in half. So if it's like 1.645, then half of that.
No, we don't cut Z-scores in half. You just cut the percents in half, the area in half.
Okay, thank you.
Because cutting the Z-score in half would be moving, let me erase something here. If I cut the Z-score in half, because remember, Z-score is a distance. Z-score is the distance, the distance we are from our mean. So if I cut my Z-score in half, if my Z-score was 0.8 something, my critical region, I would end up like over here instead. It would move it closer to the mean. Because Z-score is your distance from the mean. So since I had to cut my alpha in half, I have 2.5% above and 2.5% below. My Z-scores are going to have to be further away from the mean, right? Does that make sense? Okay,
Yeah, that makes a lot of sense.
good. I'm glad. All right, we're going to move on. Okay. After you get your critical value and you have your test statistic, we compare our critical value with our test statistic. So if it's a two-tailed test, like remember I was at like negative 1.96 and 1.96. If my test statistic is out here or out here, so basically if I had something like negative 2.15, those lie outside, then I would have to reject. If they're inside, but in between those two values, then I would fail to reject. Same thing here, left-tailed. If I end up with a test statistic that goes out here, if it goes smaller than my Z-score, so like remember we were what 1.645, so negative. So if I end up out here somewhere, so like negative 1.8, then I have to reject because of if I'm in this region right here. Same thing with right-tailed. If I end up somewhere out here with a larger Z-score, I have to reject. We'll do an example and it should help. And then I will show you my fancy calculator stuff. I like doing these ones by hand, but I know not everybody does, so I will not force you to do that. However, on the test, you don't necessarily have to do it by hand, but you have to tell me what you put in your calculator. So you write down what you put in your calculator. You would say, I used one prop Z test. Here's the values I put in for every spot on that. Because the thing is, if you showed me you did everything correct and then maybe typoed in your calculator, you're not going to lose as many points as if you didn't write any calculator stuff down at all. Because then all I would have is the wrong output. If that makes sense. All right. So let's do it. Okay. Yeah, we already did this test statistic. I don't know what I'm doing. I just did this exact same thing. Oh, wait, p-values. Okay. All right. So our p-value approach. So there's a couple of different ways of doing this as well. So our p-value approach, I recommend just using the calculator. It will give you that p-value. It will tell you the p-value. What the p-value is, it says it's the probability of getting that test statistic if your actual population proportion is what you were given. So it's just a probability. If that probability is less than your alpha, then you can reject. So I think that's what it says here. So if my p-value is less than alpha, reject the null. And the p-value is just a probability. So if your p is low, reject the hoe, as my students like to say. Then you state your conclusion. We're going to do some examples and hopefully it'll help. I know, like, I will give you all of the words in the world and they don't make sense until we're actually doing the math. So let's hopefully jump into an example. There we go. In 1997, 46% of Americans said that they didn't trust the media when it comes to reporting the news fully, accurately, and fairly. I bet that number is bigger now. Does it say that? Yes, it does. 2007 poll of 1,010 adults, 525 stated that they did not trust the media. At this significance level, is there evidence to support that the claim that the percentage of Americans that do not trust the media has increased since 1997? Even though I know it's on my next page, I'm going to write down our null and our alternative hypothesis. So our null hypothesis always assumes what we are given is correct. So my null hypothesis is that our proportion of Americans that don't trust the media equals 0.46. Our null hypothesis is that our P is 0.46. The alternative hypothesis, because we think it has increased, we would say that P is greater than 0.46. This is what your null and your alternative hypothesis would look like. All right, I'm going to jump to the next page where it's all done for me. So I want to know if P is greater than 46. We have a simple random sample. We have our NP times 1 minus P is greater than or equal to 10 to 10. And our sample size is less than 5% of the population. Okay, we're good. Here's my null and my alternative hypothesis. Here's my level of significance. My P hat is this. So I'm going to calculate a Z-score. So this right here is my test statistic. So I took my P hat, subtracted this right here, which is our mu sub P hat. And then I divided by the standard deviation. I got a, whoops, whoa, I have a Z-score. Man, that's a large Z-score. We can pretty much guarantee that that is bigger than our confidence or our critical value. So our critical value is Z sub alpha. If I look at my sheet back here, I mean, I don't need to because I haven't memorized, but 0.05, my right-tailed test is 1.645. That is my critical value. 1.645. So basically, I'm just going to draw this. So this right here, this is a Z-score of 1.645. My critical region is out here. 3.83, that Z-score is about there. We definitely can reject the null hypothesis because the test statistic z-score is significantly higher than this critical value. Questions on that? Does that make sense? Because it's outside in that critical region. I'm gonna give you a second, and then the next page is gonna give us the conclusion and all that jazz. Okay. Oops, I will do the calculator thing in a second. But I'm gonna do this part and then we'll go back to the calculator stuff. It's a right-tailed test. We have our Z, as I already said, and the test statistic is 3.83. It's greater than our critical value, so we reject the null. All right. I'm gonna go to the calculator thing, do some erasing, because I tend to draw big things. In your calculator, this is your magical calculator function right here. Stat test 1 prop Z test. This is a 1 proportion hypothesis test using Z. We're going to go into our calculators and do this lovely, lovely thing. If I can find it, went the wrong way. Always do that. Okay. Give it a second to show up. I hope I just had it up. There we go. All right. So you do stat, arrow over to tests, move my chat window. Then go down to 1 prop Z test. It's number 5. Okay. My P naught, that is the initial value I was given, which was 0.46. That's my P naught. My X value is the number of successes I had. 5, 2, 5. My N, which is my sample size, is 10, 10. And I frequently choose the wrong one of these. I'm really bad at choosing the right one, but basically I judge based on how big my probability is on whether or not I got the right one. We're looking for something to be greater than our P naught. So we think that it is greater than our P naught. So I'm going to choose that. And then I'm going to hit calculate. All right. So I got 3.81329, and it's because of estimation, but it's still a very, very large number. And we already saw our critical value. This right here is larger than that critical value. So we're good. So we can reject the null hypothesis. Questions on that? We're going to talk about the p-value in a moment. Holly, you look like you might have a question.
So the critical value is not in this.
No, the critical value is the z-score based on our alpha.
So it's and that could either be divided by 2 or not divided by 2, depending on the equation.
Yes, so the only time we divide it by 2 is when we are looking at a two-tailed test.
Okay.
The right-tailed and the left-tailed, we do not divide it.
This is where I was getting confused in my homework. I was thinking it was the P.
The p-value is also important. We're going to get to that next. All right, so yeah, the critical value you have to find on your own, but you can do that quickly with inverse norm or with the bottom of the V table, either one of those. But just be really careful with inverse norm that you know whether you need to divide it in 2 and whether you want positive or negative numbers. And it's just depending on what kind of a test it is. Sometimes drawing a diagram with that one is going to help you. All right. We're going to come back to this. I'm going to leave this here. We're going to come back to it because we're going to talk about the p-value approach next. So the p-value approach, you're looking at the probability of getting the results in your sample if our null hypothesis was true. So basically we're saying the probability of our P being of our P being, what is it, 0.525? Is that what it was? I lost it. Of our, how come it's not going? Okay, we got 0.52. So the probability of P equaling 0.52, given that our P hat, given that our P equals 0.47. Okay. I just lost it. It happens all the time. No. Why? I'm going to click out of this and go back in again. Having issues. Okay. 46. So given that 0.46, so we're looking for the probability our P hat is 0.52 if our P is 0.46. That's what that P value is. We're saying, what's the probability of getting a sample like this if this is true? That's what we're looking at. So when I go here, there's more than one way to do this, but you guys really don't want to deal with binomial probabilities, right? You want me to leave the binomial stuff alone, right? We won't go there. We will leave that out. So there's more than one way to do this, but I'm just going to stick to the calculator function. On our calculator, this value right here, this, here we go. So notice the scientific notation. Remember this E-5 means you take this decimal point and you move it left 5 places. So our probability of getting this is 0.0000686. I would say that that is significantly less than 0.05. I'm going to write this down on my p-value. On my thing, 1, 2, 3, 4, 6, 8, 5, 9. Okay. So my p-value is this right here. That is much smaller than my alpha, because my alpha is 0.05. Since that p-value is smaller than my alpha, then I can say that we basically, there's no way that we would get that p hat if the probability was actually 0.46, right? There's no way we would get that. Or so therefore we reject the null hypothesis. Questions? I think I have another example. So funny how I can forget what's on my slides so quickly when I just this morning was trying to pretty them up a little bit, and I forget that quickly. Okay, so this is a really long conclusion, but basically we're saying there's sufficient evidence to conclude that the percentage of people that don't trust the media has increased since 1997. And so I would probably say, therefore, we reject the null hypothesis. I would like you on your test, I would like you to say whether you reject the null hypothesis or fail to reject the null hypothesis. Please be clear on whether or not you reject the null. Please be clear on that. I don't care if you use a whole bunch of fancy words. You could just say the p-value was less than alpha, therefore we reject the null. If you said that to me, I would say that's awesome. You got 100% on that part. So just keep it simple. Do not get super flowery with your words. Sweet, simple, straight to the point. Just tell me my p is lower than my alpha, I reject the null, or my test statistic is greater than my critical value, therefore I reject the null. Make sense?
Calculator function.
What was that?
On the calculator function, you said that we put it less than, like we were you had to assume whether it was going to be greater than or
Yeah, so let
equals
me
to.
go back there. I always choose the wrong, I'm really bad at choosing the right one, but so the reason I chose this one is because our alternative hypothesis is that that the value is greater than the 0.46, and that's why we would do greater than P naught.
Oh, okay.
I frequently choose the wrong one, so let me show you what happens when you choose the wrong one, and this will hopefully help you, because I do it all the time and then I have to go back and fix it. So look how big my P is. If I end up with a P that's 0.9999, I can be like, wait, with this kind of a test statistic, there's no way my probability is going to be that huge. I probably chose the wrong thing.
Okay.
So you just kind of got to compare those two things and be like, okay, yeah, that wasn't right. So I always have to sit here and remember P naught is 0.46. So greater than 0.46 is the correct answer. So if you kind of put the number in there when you're reading it, it should help you.
Okay. Thank
Yeah.
you.
You're welcome. All right, let's go back there. Uh-oh. I guess we didn't. I guess we're back at 10. We're at 10.3. I'm going to I will probably grab a homework problem or something after we're done. And so I don't know why I lose these things. Sub X bar equals. Oh, no, this is a Z. Ah. All right. So we're going to use our T distribution. So our T sub alpha equals. So once again, this is 10.3 for those of you who keep track of it. We are in 10.3. And this shouldn't be alpha. This should be I'll just use a T value. So our T value here, once again, this is a test statistic. This is just like a Z score calculated the same way, but because we're using a sample standard deviation, we call it, oh, I did it again. T value equals, I thought I fixed this. Sorry about that. Because we're using a sample standard deviation, we have to use T values instead of Z values. Same thing though. We're basically calculating kind of a Z score, but a T score with our mean, our X bar minus our mean divided by standard deviation. When you are looking for your critical value, once again, this is when finding the critical value, use n-1 degrees of freedom. I highly, highly recommend using inverse T to find your critical value. Yes, you can use the T table. You're absolutely fine using it, but inverse T just saves so much time. So to get your critical value, you can use inverse T, and then use n-1 degrees of freedom. Don't forget that. And as with the Z scores, the critical values, you have to decide whether or not you're dividing your alpha in half. It's the same criteria. I don't know why does yours keep blinking black and back on? My other computer, yeah, I don't know why it's doing that. Because everything looks good here. My battery's good. Oh, wait, no, it's not. Uh-oh, hold your horses. Hold on a second. My computer's unplugged. No. I wonder if that's the problem. I thought my battery was good. Let me see where I am. Am I good? Okay, where am I? I'm at 24%. Doggone it. I fixed it. Yes, inverse norm for critical value of Z, inverse T for critical value of T. Yes, perfectly. Yes, Holly, good job. And inverse T is right below inverse norm. Okay, so let's take a look. So I'm not going to ask you about the properties of a t-distribution again. Even your quiz, it's not going to ask you about that again. Once you got past quiz 6, you're good. So I'm just going to move on. Okay. So when we test the hypothesis about the mean, it's all the same thing before. We want normally distributed. If it's not normally distributed, if the sample size is large, we're good. It's going to give you everything you need. So try not to worry about that too much. It'll give you values you can use. And so I'm not going to dig into this too deep. I'd rather stick with the nitty-gritty of the math. Left-tailed test, right-tailed test, and two-tailed test. Only difference is this is going to say mean instead of p. So this is basically the same thing. We're just using means instead of p's and using our sample standard deviation. So thankfully, a lot of the stuff stays the same. Okay. Test statistic, that's what it is, T naught. I couldn't remember. We will be given a significance level. And you compute your test statistic with X bar minus mean divided by the standard deviation. Your calculator is going to do this for you once I show you how to do that. And then you're going to use for your critical value, the n-1 degrees of freedom. I know I already said that, but reinforcing. Come on, quit being black. Quit being a black screen. It's not draining it anymore, is it? Okay. All right. Give it a second. Our critical regions look the same. We just have the t values. I'm just rushing through these because they're exactly the same thing, just with t instead of z. And compare your critical values with the test statistic, just like with, the heck is going on here? We compare our critical value with the test statistic, just like we do in z's, except for our test statistic is our t value. Okay. Do not use your table 5 to approximate the p-value. It is not fun. We are not going to do that. We are only using the calculator because it is so much more accurate. So don't even worry about that. All right. Let's go do some math. Okay. All right. I'm just jumping to the math because there's a lot of extra stuff. So we're assuming the resting metabolic rate of healthy males in complete silence is 5710 kilojoules per day. Researchers measured the RMR of 45 healthy males. This is our sample size, who were listening to calm classical music and found their mean to be 5708.07. This is my X bar with a standard deviation of 992.5. At an alpha equals 0.05 level of significance, we're looking to determine if there's evidence to conclude that the mean RMR is different than 5710 kilojoules a day. Remember, if it says different, it is a two-tailed test. So we have that our H naught is their mean equals 5710. So our our alternative hypothesis is that our mean is different than 5710. So this is a two-tailed test. All right. Let's go to the next page, maybe. Okay. Sample size is large enough. We can follow our procedures. I already said it was a two-tailed test. Sometimes I give up the answers. Let's move on. So our null hypothesis, our alternative hypothesis, level of significance. I calculate the t value this way. This is my X bar. This was the mean that they gave me. This right here is my standard deviation sub X bar. So I have a test statistic negative 0.013. I bet you that if we thought about it, we can pretty much guess that we are not going to reject the null hypothesis. I'm thinking that we all could probably get there, right? Because this is such a small t value, but still we're going to look up our critical value. For our critical T-score, I'm going to use inverse T with 0.025 and then whatever. I don't remember what's on there. Oh, and then with degrees of freedom of, what was it, 44? Oh yeah, 44. Remember, 1 minus. Sorry about that. So go ahead with your handy dandy calculator. You do second vars, go down to inverse T and put 0.025 and 44. And this will give us our critical value. Negative 2.015. And because it's a two-tailed test, it's also positive 2.015. Remember, two-tailed tests, you take both the positive and the negative. We get both of those. Did we all get those values?
Wait, inverse T,
Oh, I forgot the V. Okay, yes.
when sorry, I'm just for some reason getting confused on my calculator function.
I don't think she used the right function because I think because this is just giving us the one number. It's not giving us our parentheses unless
It won't give you two. It gives
Oh,
you
okay.
one. And because it's a two-tailed test, you just have to know it's both positive and negative.
Oh, okay. Is that what you're asking?
Yeah, that's just something you just know. It'll just give you the negative and you just have to know it's both.
So inverse T in the area is the 0.025.
Right, because I had to cut alpha in half.
Okay, gotcha.
And then you subtract 1 from your sample size. So same thing with a right-tailed test. If you put your alpha into inverse T for a right-tailed test, you're going to get a negative value. But because we know that a right-tailed test has a positive critical value, you just have to know that. You just have to be aware.
So if it's a right-tailed test, it would only be the positive value?
Yes.
Okay.
And if it's a left-tailed test, it's only the negative value.
Mhm.
Just makes sense.
Okay, so I have this thing in my head.
Okay.
Okay, so if the sign's this way, I don't know if you're seeing it backwards.
I do.
right?
Yes.
Less than. So you can literally take that sign and write less. Like ESS next to it, and it looks like an L.
Okay.
And then that little tell coming off of it is pointing to the left. So it's left tell.
Yep. There you go.
And then same with the other way. Greater is obviously not the same as, and it's right tell.
Yep.
And then if it's two tells, you have to split it twice.
You get piece.
Yeah.
Broke into 2 pieces.
Does that make sense to you guys?
Because it's two-tailed, you get pieces. I'm sorry. If that's what helps you remember that, yes, I'm all about mnemonic devices. So yes, or yeah, mnemonic devices. Yeah. All right.
I'll be on the proctored test, like doing like weird things.
I only look at things that are flagged. Don't worry.
Yeah.
You know how boring it would be for me to sit there and watch the videos of 40-something students taking their test? It would be so boring. So I just look, if it gives me some sort of if it gives me a warning, if it gives me I get alerts, it gives me like different colors, like red alerts are, they think something's really wonky, or it'll say that there was extra, that this person looked away from their screen more than other people, or whatever. I'll only look on the alerts. And usually it's just somebody's kid running through the room and they're like, get out, I'm taking a test. That's what most of them are.
Well, I'm glad you didn't watch my whole last proctored test because I cried.
Oh, sorry.
I
No, I
cried,
don't.
I cursed. I was like screaming at the kids, get out, I'm being recorded. Like,
Yeah, it's just, that's usually what they are. And I mean, I go through them pretty quickly. So
Good to know.
yeah, I would never sit and watch the whole thing. I feel like I'm invading privacy, even though I know you guys know you're on camera. I still feel like I'm like I'm violating your space if I'm actually watching it. Even when I just watch those little 10-second snippets of you yelling at your kids, I feel like I'm invading your space and it's really uncomfortable for me. But so I'm not the only one uncomfortable by you guys being filmed. You guys are too, I know. I mean, you're not the only ones uncomfortable. All right, so this was a two-tailed test. We figured out yeah, I mean, this is really close to what we got. And we estimate it with the table, and that's why it's a little bit off. But and our test statistic is negative 0.13. It is in between those two values. It is inside the okay space. So I'm going to fail to reject the null hypothesis, because it is, if I was drawing this right here, this would be negative 2.021. This is my positive 2.021. I'm in here. I'm like right here. Negative 0.013 is like right there, right to the left of my mean. So it is in the happy space. It's in the safe space. So I'm going to fail to reject. I hope my drawings help you guys, because funny thing is, I went through almost all of my schooling and I did not draw diagrams, but I find it so helpful in stats to draw the diagrams. But I mean, I'll do geometry without ever drawing diagrams. I'm really weird like that, but stats, drawing these things is just really helpful. All right.
It
I'm gonna
is,
move on. Huh?
it is very helpful.
Good.
It helps me understand it better when you draw the pictures. I know, pop-up books, whatever you have.
Good, 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 good. All right, I'm gonna move on to the P. We're gonna go do the P value with the calculator. So you're gonna use t-test on your calculator. So I'm gonna go back to the calculator if I can find it, and I'm gonna clear this out. So the t-test, if I can clear my calculator, I don't know that it's gonna be happy with me because my battery's trying to die on me. Come on. Come on. It's being mean. It will not clear. Okay, it did. Okay. So I'm going to do stat. It's going to take a minute and think about it. I thought I clicked on stat. Clear that. Stat. And then go over to tests. And we're just going to go to t-test, which is the second option. And once again, so just like with the confidence intervals, you can do a t-test if they give you data, or you can do it from stats. We have stats right now. So I have my mu naught, which was I got to go back, 5710. My X bar, which was the value that we got from our sample, 0.07. My standard deviation was 992.05. And then my sample size is, I don't remember what that is, 45. Okay. And then once again, you got to pick the right one. This one is easy because it's not equal. This was different. So this one was easy. Go down to calculate. And I got the exact same t-score. And look at that. My probability is big, but it should be big because this is like right by the mean. It's such a small t-value that there's a 98.96% chance of getting that. That p-value is definitely larger than my alpha, right? Therefore, I failed to reject. Questions?
So that T value is your T score.
Yeah, that is that test statistic that we compare with our critical value.
And then P is the probability.
Yes. The
Okay.
P is the probability of getting of our sample happening if the original mean was true. And it's a pretty good probability that we would get that value if our mean was true. I mean, that's really good. I'm hoping this is making sense. Even if it's not necessarily the math yet, because you haven't spent much time with it, I'm hoping that the idea of what's happening is making sense and the comparisons.
Okay, I need you to go over that again with me. So our alpha is 0.05, and if the t-score looks like it's larger than the alpha, then we reject it.
No, the p-value.
Okay, that's what I thought, and then I heard t and it confused me.
No, if the p-value is smaller than the alpha, we reject it. I'm gonna write this down. And it, we'll go back to the other screen in a second. Smaller than alpha, reject the null hypothesis. If p-value is larger than alpha, fail to reject. I'll go to the other screen in just a second. Okay, there you go. I wrote it down there at the bottom. I need to get this. Come on, there we go. If p-value is smaller than alpha, reject the null hypothesis. The p-value is larger than alpha, fail to reject. All right. So in this case, our p-value is greater than our level of significance, which is alpha. So we failed to reject the null hypothesis. So what all I would be looking for on a test for an answer. So they're going to give you a whole lot of words. Insufficient evidence that alpha equals 0.05 to conclude that RMR, yada, yada, yada. So all I really want from you, if you just say the p-value is greater than the alpha of 0.05, therefore I fail to reject the null hypothesis. If that's all you gave me, I'm good. I want to hear the words or read the words, reject the null or fail to reject the null. I want those words. Or even if you said, don't reject the null, I'm cool with that.
Just so I can write it in my notes of how you want it. You said p-value is greater than alpha
Yeah,
0.
I could say, since the p-value is greater than alpha, we fail to reject H naught. You can write that just like that. But come back. There we go. My battery is not being pretty on my computer. That's why it keeps going black, I think. I'm just trying to, yeah, I'm at 11% battery power. So in a minute, what I'm probably gonna do, I'm gonna have to disconnect my iPad, and because my computer will charge with Zoom on, it will not charge with my iPad connected, but I can still do this without the iPad connected. So we'll figure it out. All right. So this one right here, there's actual data that we can put into our calculator. And this data will help us to, we can calculate our, it'll calculate our test statistic for us and whatnot. So we have that according to the US Mint, quarters weigh 5.67 grams. And does it give me it gives me a, I'm looking to see if it gives me a standard deviation. Nope, but we're going to get a standard deviation from our sample. So the US Mint thinks that the quarters weigh 5.6 grams. So our null hypothesis is that our mean equals 5.67 grams. We are trying to conclude that they have a weight different than 5.67 grams. So we think that our mean is different than 5.67. So these are our null and our the alternative hypothesis. And sometimes I just can't speak. So go ahead and write those values down. And real quick, we're going to calculate our critical value. So I'm going to do inverse T, second vars, inverse T. Our area, our alpha is 0.025 again, because it's different and we're cutting our alpha in half. And I did 18 state quarters. So our degrees of freedom is 17. So I have a critical value of negative 2.10, or I'll just say 11. I'll do 11, 11 and positive 2.11. Because it's two-tailed, we need both the negative and the positive. Are y'all with me so far?
You said degrees of freedom.
Our degrees of freedom, which is DF, that's one less than our sample size. Our sample size is 18, so on the DF,
Okay, so 17.
right?
Okay.
All right. Are we good so far? Okay, I'm going to unplug the iPad while I do the calculator. That way, maybe I can get a couple % on my battery. Okay, that's why it's going black now this time. Okay, so now on my calculator, I'm going to put these values into my calculator. If you don't have it right in front of you, that's okay, because I have it in front of me. You see here if I'm charging. It still doesn't say charging, but it's not going to die as quickly. Okay. Okay, so in my L1, I'm going to put these values. Feel free to put them along with me if you don't have it in front of you. Shut down my QuickTime real quick. QuickTime. I can open it all up again if I need to. Okay, 5.67. 5.73. 5.65. 5.79. I probably missed some things. 5.7, 5.67, 5.73, 5. Okay. I totally messed up. I'm really sorry. I'm really bad at this. I don't even know why I'm so bad at this. Probably because 5.67 is in there twice, and so I jumped to the wrong spot. 5.65, 5.62, 5.73, 5.65, 5.79, 0.73, 5.77, 5.71, 5.7, 5.76, 5.73, 5.72. I'm gonna try to make this big. It's doing weird stuff on me though. There we go. All right, I'll give you a second to catch up. I love it when we have data because it can do most of the work for me. Okay, anyone need another moment? Okay, I'm going to do stat, go over to tests, go down to t-test, and we have data. So we're going to hit that. What we don't know is the mean that they gave us. That's what this asks for. So 5.67 is the mean that they gave us. We're in list L1. We leave our frequency at 1, and we are not equal to, because it said different. We are not equal to. And
I think you typed in 6.67.
I did? Okay. I believe I possibly did. Let me see. Down at the
No,
bottom?
not there where you were doing your,
Oh, okay.
Yeah,
Probably,
It should be, is it 5.67?
yeah.
yeah, it is 5.67. You know how hard it is to talk and teach at the same, or teach and then type at the same time? It's hard. They should give a class just on that, in our teaching program. How to write and teach at the same time and how to type and teach at the same time. All right, thank you. Thank you for fixing that for me. All right, hit calculate, and it does
How
all
do
the
you-
same. What was that?
Sorry, how do you know it's equal to? Like, how do you, that's where I'm confused on
What do you
I
mean,
don't
how do I
know what-
equal to?
the little meal, equals to greater
This is-
than, less than.
This is not equal to, is that what you're talking about?
No, how do you know which one to choose?
Because it says different. If it says
Different.
different, then it's not equal to.
Okay,
It could be less than, or it could be greater than. We don't know.
okay.
So would you not use not equal to for any two-tailed test?
Any two-tailed test is not equal to, yes,
Okay.
yes. All right. Once again, okay. So my T, which is my test statistic, is 2.75. The critical values that we had were negative 2.11 and positive 2.11. That number is larger. So based on that, I could say that my test statistic is 2.75, which is larger than 2.11. Therefore, I reject the null hypothesis. Or you see that I have a p-value of 0.01. That 0.01 is less than 5%, less than 0.05. That also tells me to reject the null hypothesis.
Can you give those two reasons again? You said the T is larger than,
Yeah, so
Sorry.
this is two ways to find the answer. So sometimes my open math will want your test statistic. Sometimes they will want your p-value. So these are the two ways to answer it. So my test statistic is 2.75 right here. But that value is greater than 2.11, which is what we got for our critical value. Because that is greater than that value, we fail to reject, or sorry, we reject the null hypothesis. We don't fail, we actually reject. We reject the null hypothesis because the test statistic is larger than our critical value. The second reason, the other way that we can answer this is this p-value right here is less than 0.05. Our alpha is 0.05. This value is less than 0.05. So because of that, we reject the null hypothesis. Our p is lower than our alpha, so we reject the null hypothesis. Questions?
I think it's
These are
finally clicking.
What was that?
I said, I think it's finally clicking.
Yay! And there are other ways to calculate these things, but I'm not going to show you other ways because I feel like giving you more methods is just going to confuse things. Though I will warn you, it is possible a tutor would give you a different method, but I just want to warn you. But I feel like I don't want to introduce too many different methods because I don't want you to be like, do I use this? Do I use that? What method do I use? I just want to stick to the hand calculation and the calculator calculation, and that's it. So there were a couple not important slides that I'm not going to pull up because my battery is low on my MacBook, but I want questions. I want to answer questions while we're on record if you'd like. Anything anybody has questions on while we are recording. And I'm gonna pop into, I'm not gonna, because I don't have enough battery. I'm so sorry about that, guys. but I'm not gonna solve homework problems, but I'm gonna pop in on a couple of them and we can kind of see what they're looking for. Because I know sometimes you get to the homework and you're like, what the heck is this? How does it apply to what we just learned in class? So I'm at least gonna pop in and look at a couple. Let me see what my battery is to see if I'm dead yet. It doesn't say it's charging, but I'm only at 10%. So if you lose me, I at least still have my other computer on and I'll hopefully still be able to end this. So real quick, I'm going to go to my open math. Okay. Pop into homework. And I'm going to do this while I'm still on the recording because you just never know. Let's look at 10.2 and see what we can find. Yeah, I want a teacher preview. Of course I do. All right, so I think you all can at least set up a hypothesis test. Are we feeling okay about that? Okay, this wants a test statistic and it wants a critical value. So these are proportions. So remember your test statistic is a z-score. You can use one prop z test to get that value. Your critical value, you need to use either the bottom of your your table 5, Z table, or use inverse norm to get that. Okay. See here. So same thing, critical value, use inverse norm, test statistic, use your one prop Z test. So here, sometimes, let's see if I find one of those. No. Okay, so they like to be super tricky. 0.34 times 50. I'm going to let you know that right here, you can do 0.3, your 0.34 here. This is your p hat. They like to do this because they want you to manually calculate your test statistic. It's kind of rude. However, if you end up with a nice integer number, you could find out what 34% of 50 is, and that would be your number of successes. But if you don't end up with a nice integer, then your calculator will be mean to you and it'll give you an error. So they do this because they want you to hand calculate your test statistic. So if you're not able to get it to work in your calculator, just hand do it. Okay, let me move down, see if there's anything weird. So this is another one. I wonder if 0.34 times 600, that's a nice integer. Same thing when it does that. It likes to make you do that. And look for anything weird. Remember the p-value here? This is the probability, that's that p. Be careful. If you end up with that e-3 at the end, you have to move your decimal to the left, however many places are after the e. So if it said e-5, then you would need to move it to the left 5 places. It says e-6, move it to the left 6 places. So this one right here, now this one's not very high. My computer quieted down, which tells me it's probably going to die in a minute. Okay. Yeah, this is another one, but this one should be easy because it's just 94 times 6. And there's not anything really weird here so far. These are all looking good. Your p-value, it asks if it's less than alpha or if it's greater than alpha. It asks what you're doing with your null. Never accept the null. They never announce somebody's innocent. They only say that they're not guilty. So you can fail to reject the null, not guilty, or you can reject the null, guilty. We're never innocent. You never accept the null. Okay. These all look pretty straightforward. You're just finding your p-values in your test statistics and your critical values. They all look pretty straightforward. Let me take a look at 10.3. Okay. I'm going to look at 10.3 before I get kicked off of here. All right. Okay, this is the same type of stuff. So even if I have a two-tailed test, which I don't know if I do here or not. Yep. So even if I have a two-tailed test, which this is because it says different, it only wanted the positive critical value. So be careful here when you put your critical value in. Remember your critical values on 10.3 will be inverse T. When we're dealing with the mean and just sample information, we use inverse T with n minus 1 degrees of freedom. So you subtract 1 from your sample size. Don't forget that.
And then for that one, the test statistic, what is it that we're putting in our calculator?
The test statistic, this is where you're going to, this is t-test.
T-test, that's right.
Yes,
Okay.
yes. All right. This you will actually put your data in and then use the t-test with the data. Remember your critical value you're going to get from inverse T, and your test statistic you get from your t-test with data. I believe that these are all pretty straightforward there as well. And they will be really straightforward until you're not on a Zoom with me. And then you're going to get to them and you're going to be like, everything's gone. I know this happens. And I wish I could just sit next to you and while you do your homework, I'm so sorry. All right. Because they all look like the same thing. They're looking for p-values and test statistics. Be really careful if your p-value ends up like 99%, but your test statistic is negative 2.97, you probably chose the wrong one. So if you have a really big t-value and a really big p-value, you probably chose the wrong less than or greater than. So just go back in and switch. Yeah, this one, you're just choosing what your null hypothesis is. It's having you choose whether it's mean or proportion or if it's equal then or anything. Null hypothesis is always equal. Always, always. Yes.
I have
Go
I have
ahead.
a quick question about the t-test,
Uh-huh.
the input on the calculator.
Okay.
Like I'm just looking at 10.3 on mine right now, but just making sure I feel like they don't show me, like I don't have all the information to
Okay.
input in there.
So you put in your, so if we're on stats,
Mhm.
your mu naught is whatever they think that the null, whatever null hypothesis, whatever value you have here, that's your mu naught, your mu sub 0. So whatever the
Okay.
mean that they think it is, that's what you put there. Your X bar is whatever your sample mean is. So like right here, it says X bar is 69.1. That's what you put in there.
Mhm.
And your sample standard deviation, that's right there. It gives you those two things. The
Okay.
N is how big is your sample size?
Okay.
Yeah.
Let me, okay. All right, got it.
All
Thank
right,
you.
good. Okay. Looks like they're, so the appropriate significance level here, I want to see here. What is this? I'm guessing that we're just, oh, it says right here, a 0.05 significance level. I don't know why it's asking you to identify that. I guess just pull it out of the problem. Calculate your test statistic and your p-value. It's all pretty straightforward. This, you'll put in the data and you'll use data on t-test. And it has your p-value you get from your t-test, test statistic, get that from t-test. Okay, here we go. Standard error. This is that standard deviation. So this is the S divided by square root of N. That's what your standard error is here. And I believe that it'll give it to you though. So the t-test should give you this standard error right here, but it's also, the S divided by square root of N. I'm not sure. Yeah, it looks like it's probably whatever, just use what it gives you in your calculator. Okay, that's it. So it all looks pretty straightforward for now. We'll see how it goes. That's all I have for you. I'm gonna turn the recording off, and then if anybody has any other questions, you can ask them. So I'm gonna turn this off.